This is polarization of electromagnetic waves. So when we talk about polarization, we mean direction of the electric field part of the EB wave. Okay? We're only talking about the direction of the electric field. Yes, we know the magnetic field is there. We know it's 90 degrees. It's in 90-degree angle with respect to the electric field and all that. We know that. But when we talk about polarization, all we talk about is the electric field direction. So, again, going back to this propagation of this particular way of electromagnetic wave, and I hope this drawing makes sense to everyone. I don't know if it does, but if it doesn't, please let me know. So that's the electric field, and that's the magnetic field. And those dotted lines are supposed to show you that, that's the envelope for the electric field. So if you're talking about here, it would be this. If you're here, it's this. And so I hope that envelope kind of shows what this means. But anyway, so when for this particular example, polarization is in y direction. As you can see, electric field is pointing in the y direction. Whether it goes flipping up and down and up and down, I mean, obviously, it's positive here and it's negative here because it's pointing down, and then again goes back and points up and all that. So the polarization is in the y direction. And for this particular example, it is. Okay? So if you were to look at this whole thing, I did this yesterday. If you were to look at it head on, that's my eye, then I would see the y coordinate and the z, and of course, let me take a little bit of a time and explain something the way I draw things. Do you guys know? Okay, so a vector is shown like this, or like that. It's an arrow. The length of the arrow, as we've talked about, is the magnitude of the vector, and the direction of arrow is the direction of the vector. But what if you want to draw a vector that's pointing directly into the page or directly out of the page? Are you familiar with that? Are you familiar with this notation and this notation? This is a vector going out. This is going in. Maybe I should say coming out and going in. Are you familiar with these two? No? Yes? All right. So the reason those are chosen is because in the olden times, we had arrows like this. This was the ancient way of making arrows. Okay? And they had a tail like that, and they had a tip like that. That's just the ancient way of making an arrow. If you look at an arrow head on, what you'd see is the tip of the arrow that will look like this. This is what you see. If you look at an arrow by its tail, what you see is something like this, because you're seeing that feathers that are stuck at the end of it in a cross fashion. This is why when you want to show a vector pointing at you, you show it like the one on the top. And when you want to show it pointing away from you, you show it like that thing at the bottom. Okay, this is the reason we choose these two signs to show vectors going in and vectors coming out. All right, so now that you know, I can get rid of this. That's why when you look at this electromagnetic wave, the way I've drawn the eye, you see the Y going up, you see the Z to the left, and you see the X-axis pointing at you. That's why I drew that little thing there. Okay? Okay, now, the electric field will go up and down in this direction. Okay? And this is the polarization. So the polarization is in Y direction. Okay? That is what we mean by polarization of light. It's just the direction of the electric field of the radiation. Okay? All right. Now, natural light from natural sources have random polarization. Okay, they have random polarization. What does that mean? Well, if the light is going in that direction of propagation, then the electric field is randomly positioned for maybe at this moment you measure it, it's in that direction, and then maybe at some other time it's in another direction. So it can be in all directions. So there is no, this is random direction. The electric field is pointing randomly in all directions. You don't really know which direction it is. There is no polarization. It's just a random polarization of light. This is examples are examples. You know, sunlight is completely unpolarized random. Light bulb, any you know, candle light. These are all lights that are completely random in terms of polarization. So the polarization is all over the place. It goes everywhere. So if you were to look at it head on, right, it would point in this direction, that direction, all directions. So 1/10 of a second, it's in one direction, then another 1/10 of a second in some other direction. So it's all over the place, everywhere, all angles. So there is no polarization to natural lights that we all deal with every day. But we can actually polarize that light, okay? We can polarize sunlight or the light that comes out of a candle or a light bulb. We can actually do something to it to polarize it. Okay? We can use polarizers to polarize unpolarized light. Okay? And polarizers are, special. There's all sorts of ways you can make a polarizer, but usually it's a piece of plastic. It's a sheet of plastic that has been pulled in one direction. Okay, so it has this polarization axis. Usually you show it like that. So this is the polarization axis. Okay, and I don't want to get into details of how this sheet of plastic polarizes the light. All you need to know is that there is a direction to that polarization sheet. And whenever you have an unpolarized light coming in with its electric field all over the place, okay, when it passes through and comes out, the electric field would be exactly lined up along the polarization axis of that polarizer. So what comes out is actually in that direction. Okay, and of course it flips up back and forth. So you can see, let me see if I can draw this a little bit better in terms of parallelness. Oh. So it would be like that, So whenever you have a polarizer, depending on the direction of that polarization axis, what goes through is exactly parallel to that polarization axis. Any other direction will not go through. So only that portion of the incoming electric field would go through that is exactly in the same direction as the direction of polarization of the polarizer. Okay, so this is if this is random. So natural light, so you can always go buy a polarization sheet or a polarizer. Polaroid makes glasses out of polarization sheets, out of polarizer glasses. So, and there's a reason they do that. But anyway, you can always go ahead and buy, I'm sure you can find these things online these days. You can get sheets of polarizers and play with them. Okay, you can actually polarize light that is not polarized. Okay, so only the portion, the component of the electric field parallel to polarizer axis. Okay, only that one comes out. All right, so that's how a polarizer works. You can actually polarize natural light to get a polarized light. Now, suppose you already have polarized light. My handwriting. Okay, suppose you already have polarized light. So suppose it's, it's just pointing some direction. All right? And let's define some axes here. Okay. So, and then I'm gonna have a polarizing sheet here. And the polarizing sheet is going to have, I don't know, its polarization axis up. Okay? And now I'm going to go ahead and look at this whole thing head on, like that. So what I'm going to see is then this. Okay? And then I'm going to see the electric field like that, because it's already polarized. And then I'm going to have this sheet be all over the place with its axis in that direction. Okay? So, we already know what happens. Only the component parallel to polarizer goes through. Okay, well, let's break up that electric field into its components along the polarizer axis and perpendicular to it. Okay? All right, and I'm going to call this, so this is the E parallel, this is the E perpendicular, and I'm going to call this angle theta, right? And then I'm going to go ahead and say, if I have a polarized light already going through a polarizer, the only thing that comes out is this thing, which is from this right triangle is the magnitude of the electric field that is going in times the cosine of the angle. Okay, so that's the that is what comes out. So what comes out is this E parallel. Okay? Now, you can imagine if you rotate the polarizer such that the angle theta is exactly 90 degrees, what are you going to see? Right? So if I turned the polarizer, so here's my electric field, and if I had the polarizer rotated like that with its axis this way, what is the thing that comes out? That's exactly right, and you can actually see it from the drawing. The electric field in this case has nothing, no component parallel to the axis of the polarizer. Obviously, when nothing comes out, you see nothing. So no light can go through anymore. That's correct. And you can also do it mathematically by setting theta equal to 90 degrees, you're going to get 0. All right? And then the intensity of the light that passes through, the intensity of light that passes through is, of course, we already did that. It was E squared over 2c mu naught. This we did yesterday. This is the intensity of any light that comes through. But then what passes through is the E parallel, okay? And that is E squared cosine squared of theta over 2c mu naught, okay? Or I can write this as E squared over 2c mu naught times cosine squared of theta. But this thing in parentheses is just the intensity of the light before it goes through the polarizer. This is the original. Okay? So now you can see that this thing that goes through is equal to the original intensity times cosine squared of theta. And so whatever you see, I mean, you can always plot this as a function of theta. And you're going to get a cosine squared. So this is 90 degrees. And this is 0, of course. So depending on the, so if you, let me go back and recap. This is true when you already have a polarized light coming in. Okay, this is polarized light already coming in, and then you're going to put a polarizer in front of it, and then you can rotate the polarizer in front of it and get between 0 and maximum value of the intensity, depending on what the angle of that polarizer is with respect to the orientation of the electric field in the polarized coming light. Okay, so that's the that's what a polarizer does when you already have a polarized light. What if you don't have polarized light? So this time, the electric field is all over the place, not polarized at all. And then I'm going to put the sheet in front. Okay. What am I seeing out here? That's my eye. What am I seeing? This time it's not polarized. When it was polarized, I would see this on the top. This is when incoming is polarized. All right, but what if it's not, like the one at the bottom? What am I going to see? There's still intensity here. There's this intensity of the light that's coming in. What is the intensity here? What is it? Any guesses?
Would it just be of the one that's directly parallel to that?
Yeah, but the intensity of incoming light is measuring all those electric fields at all those directions, right? So what would be the intensity that goes through if it's not polarized anymore?
Infinity?
Really?
That's wrong. I'm sorry.
When you say infinity, that means it's so bright it's going to blind you. Does that make sense? All right. What if I look at the plot on the top? If it were to be polarized, you would see the intensity depends on the angle. But now you have all those angles down there. So what is the thing that's you're seeing? Right? What you're seeing is all those angles. So you would see an average value of the intensity drawn on the top. What is the average value of that intensity? What is the average value
Is
here?
it one half of the original intensity?
That is correct. That is correct. I that goes through now is the average value of a cosine squared function, which is usually just 1/2. Well, it is always 1/2, not usually. So you see, when you have a polarized light already, you know the exact angle between that polarization and your polarizer, then you get that function on top. But if that angle is all over the place, like an unpolarized light coming in, then you get the average value of cosine squared, which is 1/2. So the intensity of the light goes down by a factor of 2. It's exactly half of what goes into the polarizer. So when you get a polarizer, if you ever have seen a polarizer, it looks gray because whatever light that goes through it, it gets cut by 1/2. That's why it looks gray. Half of the light that goes through it gets lost. You only get half of the light coming through it. So that's the relationship between that's the difference between having a polarizer in front of an unpolarized light versus a polarized light. Okay? All right. All right. So let me talk about reflection and refraction. All right, reflection and refraction. All right, so suppose light goes from one medium to medium 2. Okay, now, as far as optics is concerned, or any electromagnetic wave, when you go from one medium to another, the mediums are all defined by an index of refraction, which is usually denoted by n. So the medium 1 has index refraction of n1, medium 2 has index refraction of n2. You know, this is examples are maybe air here. Air is this one, and maybe this one is glass or water. All right, and you guys have seen how light goes from air into water or glass. So if the electromagnetic wave, in this case, say light, if it's coming in this way, and we always measure the angle of incident as the beam of light make an angle with the normal to the surface. So this is the normal to surface. Okay. What happens here is that the light gets reflected first. This is, let's call it 1. reflected. And then it also refracts in. This is refracted. Okay, and then we also measure that angle with respect to the normal. Okay, so there's this incident angle, and then there's this reflected portion, and you guys have all seen the surface of glass or surface of water reflects some of the light. And some of it goes through, obviously. And so the law of refraction then probable reflection says the incident angle is equal to the reflected angle. So you can see the two angles are exactly equal for reflected beam versus the incoming beam. Okay? Now, the law of refraction is obviously different. And that one is N1 sine of the angle incident is equal to N2 sine of the angle refracted. Okay, so these two you want to know by heart. So let's, we can actually do some examples and to see how these two rules govern when light passes from one medium to another. Okay. Just for to give you some physical sense of what is the index refraction of different medium. Vacuum is exactly 1. Air is roughly 1. It's a little bit larger. It's usually of the order of that. It's a little bit larger than 1. And there's all sorts of other indices. Diamond, it has one of the largest ones, 2.42, and so on and so forth. And everything else is in between. Glass is 1.5 and things like that. A glass is 1.5. I think water is about 1.4 or something. Okay, so these are indices of refraction of different materials. These are constants. They only depend on the material. So only depends on material. So, vacuum is always 1. Glass can be, mixed with all sorts of other things. But diamond is 2.42. Water, if it's pure, is around 1.4, and so on and so forth. So when they're giving you a problem, they usually don't tell you what the index is, even though I will. Maybe they say, okay, light is going from air into diamond. Then you have to go dig out the diamond's index of refraction to be able to solve the problem. Usually in the problems, they tell you these things. Sometimes they don't. But then if you go through the book, you see a chart that gives you all these, all the information. All right, so let's do one quick example. Okay, so suppose this is 1.5, and this is 1. So it's like air going to water or something. All right, and suppose the angle is 30 degrees. And of course, reflection would be also 30 degrees. That's just the first rule of reflection. But what is this angle? What's alpha? Okay. Well, law of refraction says N1 sine of the incoming light is N2 sine of the outgoing one. Well, in this case, I've called it alpha, so we'll call it alpha. So sine of alpha then is N1 over N2 sine of the angle of incoming. And N1 is 1, and N2 is 1.5, and sine of 30 degrees is 1/2. So this is 1.1 over 3. So alpha would be sine inverse of 1/3. And of course, I don't know what that is. I have to go to my calculator. So 1 divided by 3 is that. And then sine inverse of that is 19.5. Okay? So you can see already in this example, simple example, that the angle alpha is smaller than the incoming angle of 30 degrees. Okay? So, one of the rules of refraction then is N1 and N2 theta n and say 2. Theta 2 is smaller than the angle if N1 is smaller than N2. So that's one of the rules. Now, if you do this problem again, and this time you let the N1 be larger, you'll find out that theta 2 is larger than theta 1 if N1 is larger than N2. So you can see there is this, so this is usually if the example here would be IE air to IE water. Here would be IE water to air. Okay? So if you're going in to a larger index, like the one on top, you're going to get closer to the normal angle, to the normal direction. If you're going in to a smaller index, then you're going to be away from the normal direction. Okay? So you want, and we'll talk about, this is going to become important soon. Of course, we ran out of time. Let me go on another minute or two, but then we'll stop after that. Okay, so you want to remember this thing. This is going to be important later. Okay, now, not only that, there is a thing called chromatic dispersion. I don't think there's two S's here. Okay, this is a little bit of a fancy scientific word. Chromatic means colors, and dispersion means spreading. So what this really means is that the index of refraction of any material is actually a function of wavelength. So index of refraction is a function of wavelength. Okay? So if you were to plot index as a function of wavelength, usually you find something like this. Okay? Where, you know, this is just an example. Maybe this for water goes on 1.5, and by the time it gets here, it's 1.4. And this is the wavelength of, say, blue, 380 nanometer. Maybe by the time it gets to red, the index goes to like 1.35 or something. So you can see the index of refraction is a function of wavelength of the light that's coming in. Now, we had never heard of this before. Now this is the first time. Because this is going to have implications. It means if I go from air to some, say, water or glass, and if there's dispersion, what happens is as you can see, the blue has a larger index. The blue part is going to go like that. And the red one is going to bend less. So this is what dispersion does. When light goes to another medium, because that medium's index depends on the wavelength, each wavelength is going to be bent differently because they see a different index of refraction. In this case, the red is going to see this, and the blue will see that. This is the index for blue, and this is the index for red. And if you use those equations, you see that different numbers will give you different angles. All right, we'll continue tomorrow. Let me get the screenshot here.
Can I talk to you real quick after everyone leaves?
Sure. And you can also